I've met you guys. Chris is now at Oxford, Andre is a professor at Utrecht, and well, they're going to be talking about quantum groups and three-manifold invariants. Chris is going to start today with 2 lectures on topological field theories in dimension 1 and 2.
Thank you, Raimundo. That is, by the way, completely not true. We've been going to the beach every day. Just because Raimundo doesn't come to the beach with us every day. Yeah, so as he said, I'm going to start this hour talking about topological field theory in dimensions 1 and 2 as kind of a warm-up. So let's just start with some preliminary definitions. So what is a topological field theory? Well, the first thing we're going to start with is a category of manifolds. So I'm going to write it toward d-1d. So the objects are d-1 manifolds, and the morphisms, so the objects are d-1 manifolds. You know, say a circle, and the morphisms are d manifolds that are bordisms between these d-1 manifolds. So for instance, this might be a morphism from the circle to the circle. And then the composition operation is gluing. That is, you take one morphism and then you glue it to another morphism along their common boundary. And this also has an operation of disjoint union, which is a monoidal structure. So there's a monoidal structure, which is disjoint union. So if I have 2 circles, I can just put them next to each other. So this whole thing is a symmetric monoidal category. And actually later this hour, I'm going to define precisely what a symmetric monoidal category is. But for now, just think it's some category together with some commutative multiplication operation. So this is kind of the geometric situation we want to study, and the way we're going to study it is by mapping it into some algebra. So in particular, vect is going to be our target algebraic category for now. So of course the objects are vector spaces, and the morphisms are maps of vector spaces, and composition is, well, composition of maps of vector spaces. And then the monoidal structure we're interested in is the tensor product. So this is also a symmetric monoidal category. And so getting right to it then, so a topological field theory in dimension d-1 to d is a symmetric monoidal functor from this geometric category to this algebraic category. And again, I'll say what I mean precisely in a bit, but again, it's just some functor that preserves this commutative multiplication. So a few notes. So what are the units? So this multiplication operation has a unit in both these categories. So the empty manifold is the unit in the bordism category. If you take the disjoint union with the empty manifold, you get whatever you started with. And of course, the complex numbers is the unit with respect to tensor product in vect. And so what does this mean? It means if we start, suppose we start with a closed D-manifold that has no boundary. So a closed D-manifold is some morphism from the empty manifold to the empty manifold. So this gets mapped under our topological field theory Z to some morphism from the unit to the unit, from C to C. So this produces some map from C to C, which we can just think of as multiplication by some complex number. And so that is the topological field theory gives numerical invariance of closed D manifolds. So that's the kind of general setup. And so now let's get started with warming up with dimension 1. So dimension 1 topological field theories. Let me know if either I end up writing too small or if my handwriting becomes unreadable, and I'll make an effort. So given some one-dimensional topological field theory like this, and so I'm now actually going to implicitly think not just about any manifolds, but about oriented manifolds. So I'm really thinking about the oriented Bordism category. So all the manifolds come equipped with an orientation. What does that give us? So let's look at where various manifolds go. So suppose we start with a positively oriented point that gets sent to some vector space, which I'll call V, and then the negatively oriented point gets sent to some other vector space, W. And now what kinds of Bordisms do we have between zero manifolds? Well, here's a Bordism from the empty manifold to the disjoint union of a negatively and a positively oriented point. And so this maps to some map from C to V tensor W. And then I could take a cap Bordism like this the other way. And this gets mapped now to some, So this is the positive and the negatively oriented point, and so this gets mapped to a function from W tensor V to C. And so now we can start thinking about how these different Bordisms compose and see what kinds of algebraic conditions that imposes on the vector spaces that they end up with. So for instance, so these various maps satisfy some conditions. So for instance, if you glue together this Bordism and this Bordism along this point in the middle, well, this is Bordism from one point to one point, but it's diffeomorphic to just not doing anything. And so here this was plus and plus. And similarly, if I'd instead started with the negatively oriented point, this whole thing is also equal to not doing anything on the negatively oriented point. So let's see what that leads to in algebra. So this equality here, well, by construction, I know that these things compose well, so I can split this Bordism into two pieces and then write down the composite of those two pieces. So what do I have here? Well, let me give these maps names. So let's call this the co-evaluation map and this the evaluation map. And so to start with, I start with my vector space V, and this gets mapped to V tensor W tensor V. I'm going to write it vertically just so it's parallel to that, where I essentially mapped C into these two factors here. And then so those went there, and then these two factors map out to C, and that factor stays V. So this whole thing produces a map from V to V, and that composite is supposed to be equal to the identity on V. And similarly, I won't write it out, but you can write down the corresponding equation for W. And this is basically encodes exactly the notion of W being the dual vector space to V. So let me write that down. So will do. Okay, so suppose C is some general monoidal category. then we say that W is right dual to V if we're, well, given exactly this setup. So if there exists some map, well, there exists a map from the unit of the category 1 to V tensor W, and a map from V tensor W, oops, sorry, I got one of those backwards, map from W tensor V to the unit, which I might draw suggestively with these Bordisms, such that these two zigzag equations hold algebraically. So by this, I mean, it's a little bit confusing maybe, but by this I just mean a shorthand for an actual algebraic equation written down in the category in terms of V and W. I just won't write it out again because I wrote enough here. Okay, so that's the notion of a dual. So just as a comment, in the same situation, we say that V is left dual to W, and we might write W equals V star, or sometimes use this adjoint notation here. This notation, W is equal to V star, is a little bit dangerous because you really need to remember these co-evaluation and evaluation maps to pin down the notion of the dual. So it's dangerous to just remember the vector space. But anyway, so a small exercise. So when I write EX, I'm going to mean exercise, not example. So if C is symmetric monoidal, so if this operation is actually commutative and W is a right dual to V, then W is also a left dual to V, which I could say instead V is also a right dual to W. So in a commutative situation, these two notions, well, the same vector space functions as both a left and a right dual, or the same object, rather. Okay, so now it turns out that having a dual is actually a very strong constraint on what this vector space can be. And so having a field theory whose value is this vector space can only happen if V satisfies a condition, and that condition is being finite dimensional. And we'll see more complicated analogs of this condition as we go along. So the proposition is that V has, so now I'm thinking about V, an actual vector space, has a dual. Vect is commutative, so I didn't have to say left or right dual, if and only if V is finite dimensional. So let's actually prove this. So first of all, let me assume, I'm going to go through this chalk very fast. Let's assume that V is finite dimensional and prove that it has a dual. So I can just define the vector space that's going to be the dual as Hom from V to C. So this fits with our usual notion, and I just need to provide for you this co-evaluation and evaluation maps. So what's the co-evaluation? So I'm mapping here to V tensor V star, and I just send 1 to, I pick a basis EI, and then some dual, write down the dual basis EI star, and I sum those up. And then, on the other hand, the evaluation map is just what you expect. It's actually evaluating the function on the vector. And maybe I'll leave it to you to check that that actually does. Oh, I make a comment about shock, and Raimundo shows up with two big handfuls of it. Okay, so again, just to be clear, what I meant by this is that the EI star evaluated on EJ is delta IJ. And I'll leave it to you to check that that does actually give a dual in the sense that these two equations are satisfied. So what about the other direction? So now we're given a dual. And so let's actually write down. So we're given the dual together with its co-evaluation map. So now we don't know what this vector space is, so all we can say is that 1 goes to sum of V, let's say EI tensor FI, probably. And now it's going to be important for me to keep track of the fact that this was sum from 1 to n, because this is a tensor product, so the elements in it are finite sums of elementary tensors. And then the evaluation map was sum map here from W to V. And let me just write that F tensor E maps to F of E. I, of course, I don't really know what W is, and I don't know what this function is, but I'm just going to write it by analogy with the usual evaluation. And so now let's use the basic duality equations. So if I start with V, so let me use the zigzag that started with V. So you can think about this zigzag here. So I start with V, and I first do a co-evaluation. So this is this zigzag. Let's write it out. So I start with V, and I first do this co-evaluation. So I now have the sum from I equals 1 to n of E. Bigger, sorry. Yeah, just keep reminding me at regular intervals. So I have the sum of EI tensor FI tensor V, and then I evaluate the last two factors, and so this goes to FI, well, sum of FI of V times EI, again from I equals 1 to n. But by the basic duality equations, this is the identity, so this is just the vector V. And so now, what have we seen? We've seen that the whole vector space V is spanned by these vectors EI for I equals 1 to n, and so that directly implies that V is finite dimensional. Okay, and so this is hopefully going to be motivating for Andre's talks, because in higher dimensions, we're going to be looking for more categorical analogs of this finite dimensionality condition coming out of quantum groups. Okay, so what's the sort of summary of what we've done so far? So what we saw, essentially, is that if we had a TFT, then the image of the point was some finite dimensional vector space. And on the other hand, if we had a finite dimensional vector space, we could just write down all of this data, and it would indeed give a TFT. So summary is that oriented one-dimensional TFTs exactly correspond to finite-dimensional vector spaces. This is kind of the simplest classification result in this context. Okay, and so now once we have a TFT, well, the claim was we could get some numerical invariance out of it. So there aren't very many interesting one-manifolds, but we might as well compute the one we can. So suppose that, I guess I've been calling it Z is my TFT, so we can compute its value on the circle with that orientation. So it's convenient to rewrite the circle as this figure 8 because I sort of presented my elementary pieces in this in a way that'll be more convenient for that, and then we can chop up Z in this way. And so now let's see. So this very first piece, hopefully I did even have the orientations the same. So this very first piece sends 1 to the co-evaluation on 1. So that's sum of EI star from I equals 1 to the dimension of n. And then we have to apply the rest of this Bordism. And so now then we apply the next piece, which is just twisting these two factors. So then we have sum of EI star tensor EI. And then we're going to have this very last piece, which is the evaluation. And so this now becomes the sum of EI star of EI. And this is just 1. And so we're just summing 1 from 1 to n. So this is exactly the dimension of V. So that's pretty much all there is to say about oriented one-dimensional field theories. That's the invariant and the classification. So that's it. How are we doing on time? Okay, so let's now step back and I'll say a little more precisely what some of these monoidal structures are. So that is these monoidal structures on categories. So first of all, let me say what a monoidal category itself is. So C is a monoidal category if, well, it needs to have a multiplication. So if it has a functor from C cross C to C, which I'll be denoting tensor. And on objects, I'm just going to write it as juxtaposition A cross B goes to AB. And then it needs to have, so the issue is because we're in a categorical setting, we don't want to just demand strict associativity. We want some kind of weak associativity condition, which is going to be given by a natural isomorphism ways of multiplying 3 objects. So if I have 3 objects, I can multiply these 2 and then the third one, or I can multiply the last ones and then the first one, and there ought to be a natural transformation called the associator between those 2, which I'll denote. So I'll denote this natural transformation just by its behavior on objects, so sort of as a line between these 2 different ways of multiplying 3 things. And then it should have a unit. So it should have some object called 1 in C, which is going to function as a unit. And then it needs to have some natural transformations that say that this is the unit. So it should have naturalized morphism. I can map to C cross C by putting the unit in the first factor and then multiplying them together. Or I can put the unit in the second factor and then multiply them together. And these should be the same as doing nothing. That is, if I take 1 times something, it's the same as not doing anything at all. And then these need to, so that's all the data, and then I want these to satisfy some coherence conditions. So continue over here. So the main coherence condition on the associator is the pentagon condition. If I have 4, let me start here. If I have 4 things, I can multiply them in many different ways, and I can use the associator to transform between those different ways of multiplying, and there are different paths I can take through the possible multiplications, like this. And those different paths form a pentagon, and so these are natural transformations, and I demand that this diagram of natural transformations commute. And then there's some more conditions that are coherence conditions for the unit that I won't write down. They come in the form of 3 triangles that constrain the unit, and I won't write those down. Okay, so that's the end of the definition of a monoidal category. And now I also want to say what it means to have a symmetric structure on this category. So C is some monoidal category. C is symmetric monoidal if it also, in addition to all of that, has a symmetry operation. So what's that? So if I have 2 objects, I can switch their places, just putting the first one in the second place and the second one in the first place, and then I can multiply them. Or I can just multiply them straight off, and I want a natural transformation tau between those 2 different things you can do. So concretely, it just gives you some, if I start with some object A and B, or A cross B, say, this natural transformation goes to some transformation from some isomorphism from AB to BA. So it provides a specific isomorphism from multiplying one way to multiplying the other way. Sorry, I realize it's getting a little small again. Okay, but we need this transformation to satisfy some coherence conditions, as you might imagine. And those coherence conditions come in the form of 2 hexagons. So let me say what those are. So suppose I started with multiplying 3 things, A, B, and C, then what are some of the different things I can do with all the structure I have? Well, the first thing I could do is I could switch A and B to BA, C, and then I could reassociate this to BAC, and then I could switch A and C to get BCA, and then reassociate back to get BCA, or I could associate over to get ABC, and then switch the composite BC past A. So this seems a little abstract, but basically we're just thinking about so here's the picture to have in mind that you can then reproduce this diagram with. So I'm starting with 3 objects, which I think of as little strands. And on the one hand, I can move the first two strands past each other and then bring in the next strand and move it past that first strand. Or I can put these last two strands really close together and just move them past the strand all at once. So in the picture, I've suppressed the associators a little bit, but I've kept track of kind of which things I'm braiding past which other things. And there's a second hexagon condition that I won't write down, but it corresponds instead to this picture where I first braid two past from the left, or I braid first one and then the other. Okay, so we're not quite done with this definition, so I'm continuing the definition over here. So, and there's one more condition, which is that tau squared is equal to the identity. So if, for this to be a symmetric structure, if I switch once and then switch again, that needs to be the same as not having done anything at all. Okay, so that was the end of the definition. But if I'd omitted that very last part, if I just had this much, then that's what's called a braided monoidal category, which is going to come up a lot during these lectures. And you can start to see why it's called a braided monoidal category by these pictures. And what does this last condition say? It says, well, if I braid something twice, that's the same as not doing anything at all. So it didn't really matter, these over and under crossings. But without this symmetric condition, the over and under crossings matter a lot, and you really are seeing these kinds of braids. Okay. So that's monoidal categories and symmetric monoidal categories. So now we have a more precise idea of what the symmetric monoidal structure on the Bordism category and on vect means, but we also wanted some functor between them. So we need to know what it means to have a monoidal functor. So write that down. So a monoidal functor, let's see, I think C and D. So let me call it F. So C and D are monoidal categories. This is a monoidal functor. Well, is a functor, and then it also has following naturalized morphism, which is, so if I start with two objects of C, sorry, I guess I'm calling it C. What can I do? Well, I can apply F cross F to move over into D cross D, or I can multiply and then move over, or I can multiply in D, and I want to have a natural isomorphism between these two different ways of doing something. And so again, all these definitions are just modeled on the normal ones from algebra. If you wanted some map of abelian groups, if you wanted a map of groups, then you want it to preserve to be a homomorphism, and that's what this is saying. But again, we want some more conditions, so we need to have a condition for the unit as well. So there's some unit in D, and we want a specified isomorphism between that and the image of the unit in C. So it's essentially saying that the functor preserves the unit. And then these things need to satisfy some coherence conditions that maybe I won't write out. So you probably are getting the hang of how to write down these different conditions. So there are 3 conditions. One has the shape of a hexagon, and there are 2 squares, so maybe I'll leave it as an exercise to think up what the natural coherence conditions are for a monoidal functor. Okay, but we really wanted a symmetric monoidal functor, so we need to keep going. Well, and in fact, as long as we're on the way, let's say what a braided monoidal functor is, because we're going to be using braided monoidal categories a lot. So if we have some functor here is braided monoidal, if, well, we need C and D themselves to be braided monoidal, and then we need to satisfy just one coherence condition. So suppose we have 2 objects of C, A and B. What can we do? Well, on the one hand, we can move them into D, or right. So the fact that this is a categorical homomorphism gives us a map from f of AB to f of A, f of B, or we can use the braiding to switch A and B and then apply the functor to that transformation, and then we can split those apart, or we can use the braiding in the target D here, and we demand that that commute. We're almost done with these boring categorical definitions. So just to be clear, that's tau, and this is f of tau. So this is the braiding tau in C, and this is the braiding tau in D. So now what's a symmetric monoidal functor? So C to D is symmetric monoidal if, well, C and D are themselves symmetric monoidal, and the functor f is braided monoidal. So there's actually no further condition for it to be symmetric monoidal other than the one we already imposed for it to be braided monoidal. Okay, thank goodness. So that's the end of the category theory, and now we can go back to geometry now that we at least have a precise notion for all of these structures and the functors between them. So we did dimension 1, as I'm now erasing. So let's move on to dimension 2. So let's think about two-dimensional TFTs. So what's a two-dimensional TFT? Well, by definition, so we're looking at the Bordism category whose objects are one manifold and whose morphisms are two manifolds, and we're looking at symmetric monoidal functors in vect. So let's think about what kind of information this gives us. So we have a circle that goes to some vector space V, and then now we can do some more interesting things. So now we have, for instance, this two-manifold that is a Bordism from 2 copies of the circle to 1 copy of the circle. And, well, that goes to some map from V tensor V to V. Again, I'm implicitly going to be thinking about oriented Bordisms, even though I won't actually draw that. So what are some other Bordisms we have? Well, this is meant to be a picture of a Bordism from the empty manifold to the circle. It's just a little cup there on its side. So this maps to some map from C into V. And now you can start playing around with how these Bordisms glue together. So for instance, if I take this cup and stick it on the end here, then I am left with a manifold that has this protruding tail, but I can just take a diffeomorphism that shrinks that tail back into an ordinary cylinder, so I get the identity. And so that tells us that in the target, this map is actually functioning as a unit for this product structure on V. And similarly, I took 3 circles. I could glue them together and then glue in the third one, or do it the other way around, and those two manifolds are diffeomorphic. And so altogether, these structures form a unital associative algebra. It occurs to me that maybe I should have been a little more precise when I wrote down the definition of the Bordism category in the first place. You know, I said, well, the objects are D-1 manifolds, so here 1 manifolds. And I said the morphisms are 2 manifolds, but really I wanted to mod out by some equivalence relation on the 2 manifolds. So I wanted to mod out by diffeomorphisms rel boundary. So if I have 2 manifolds and they're diffeomorphic without touching the morphism in this Bordism category, and that's why I can do those little computations that I just said, where I have a diffeomorphism that actually sets 2 morphisms to be equal in the target category. So you can play the same game, of course, going the other direction. So if I have a Bordism this way, then that goes to some map from V to V tensor. This cap, this morphism from the circle to the empty set, gives some map from V to C, and together these form the structure of a co-unital, co-associative, co-algebra. So this is already a kind of interesting structure. So I have one vector space, which itself is equipped both as an algebra and a coalgebra. And so now, well, it's inconvenient, but I'm going to go over and think about how these different structures interact with each other. So, for instance, we can start, well, actually, before thinking about how they interact, let's think about the commutivity properties of both of them. So, for instance, if I start with 2 circles and I switch them, and so now I have 2 circles here, and then I can multiply those together. I could compare that to just multiplying the 2 circles together directly. And these 2 Bordisms are diffeomorphic rel boundary, and so they're actually equal in the Bordism category. And so that means that, well, the twist and multiply on the vector space is the same as just multiply. So the algebra structure on V is actually commutative. And similarly, the on V is co-commutative. Okay, so now let's think about how these 2 things interact with each other. So suppose I again have 2 circles. Let me draw this a little further down. So if I have 2 circles, I can first multiply them together and then co-multiply back out. Or starting with those same 2 circles, I can first, say, co-multiply the second one, and then multiply like that. Or there's a third thing I could do, which is that I could co-multiply the first one and then multiply in the second one. And all three of these are diffeomorphic REL boundary, just by squishing them around a little bit. And so that imposes some, so this whole business imposes some over on V. So on the one hand, if I had, so let's just write it out. If I had V tensor V, I first multiply and then co-multiply. Or up here, it was the identity tensor, the co-multiplication delta, going to V tensor V, and then I multiply the first two, which I'll call M, tensor the identity, or going the other direction, I did delta tensor the identity, V, and then I did the identity tensor the multiplication. And so these are equal, so I want these composites to all be equal, and this is the definition of a Frobenius algebra. So a Frobenius algebra is a unidal algebra that's a co-unidal coalgebra such that these conditions are satisfied relating the algebra and the coalgebra structure. Okay, so a small exercise. So suppose you have a unidal algebra that's also a coalgebra, and it satisfies not the whole Frobenius condition, but it just satisfies this top composite is equal to the bottom composite, so such that that composite is equal to that composite, then show that it is actually Frobenius. That is, that the other equality is automatic. Okay, so where are we? So we've seen that if we have a two-dimensional TFT, then the image of the circle is some vector space that has the structure of a Frobenius algebra. Maybe I'll write this down as a summary as I did before. So again, I have thinking about oriented two-dimensional TFTs and claim that these correspond to finite dimensional commutative, co-commutative Frobenius algebras. So we've seen the Frobenius algebra and the commutative and the co-commutative part. So what about the finite dimensional part? Well, basically the same argument we gave in the one-dimensional case also works here. So the claim is that this vector space V has, which happens to be V again, using these sort of snake boardisms. So these boardisms, well, really I should have just talked about those two boardisms, which give the evaluation and co-evaluation for duality that you then check by checking that snake is diffeomorphic to the identity. So if he has a dual, so the same argument as before shows that it's finite dimensional. So now, as before, we have the classification. So let's write down what invariance of two manifolds we get out of this situation. So the first one well, the first thing we might want to evaluate on is the torus. Well, okay, it's not the first thing. I guess it's the second thing. So what is the value of the field theory on the torus? Well, let's split it down the middle. So we have the co-evaluation for this duality, and then we're composing it with the evaluation. So exactly the same computation as we did for the circle tells us that this is the dimension of our Frobenius algebra, that is the value of the circle. And now, to compute the values of these invariants on other surfaces, we can make the following observation. So there's some bordism from a circle to a circle that has genus 1. And so this is some map from, let me call it V again. So let's say that's V. So this is some map from V to V. And I claim this morphism is multiplication by a certain element, namely the value of the theory on this once punctured torus. So this is a map from the complex numbers to V, so I can think about it as an element of V, and I'm claiming that this map here is multiplication by that element. So why is that? Well, because this is diffeomorphic rel boundary to this surface. So I took whatever I was starting with, and then I multiplied in this thing, which is called the handle element, and it's the same as that surface, so that shows that. So then we can use that fact to compute the value of the bordism on any surface. So suppose we have a surface, some genus G surface. Well, we can use these handle elements to create all of the topology. I guess I didn't name any of these things, but this map from V to C I'm going to call epsilon. And so what do? Well, I create G holes by multiplying together this handle element G times. So actually, let me define this H, this handle element, and then I take the epsilon trace. So I started with 1, and then I multiplied H together G times, and then I traced it off. So this now gives us so this is a general formula for computing the invariance, which I'll do in an example in just a sec. But before I do that, just a side exercise, which is that, in fact, a lot of the structure of the Frobenius algebra is determined. So the exercise is to show that the multiplication and this co-unit, that is epsilon, determine the whole Frobenius algebra. So it's a fun exercise. So now, we have time for just one example, maybe. So I guess I'm going to use EG for example. So let's look at the following algebra: C adjoin T mod T squared minus 1. So that's going to be the unidal algebra, and so then I need to tell you also, well, according to this exercise, all I need to tell you is what the co-unit is to specify the Frobenius algebra. So with the following co-unit, so map from V to C that sends 1 to 0 and sends T to 1. So first of all, I claim that it is a Frobenius algebra. Yeah?
Is it knowing the isomorphism between V and its dual? You give me a vector space with a commutative address product and a counit, and you claim it's a Frobenius algebra?
Oh, no.
Should I be able to recover the whole thing?
Well, I didn't claim it is necessarily a Frobenius algebra.
Well, let's suppose it is, then I should recover the structure
Yes.
by only knowing the multiplication and the counit.
Right.
Can I get some information as the isomorphism between V and its dual? I'm surprised me, that's it.
Well, we can try to do the exercise after class. And so in this particular case, well, maybe we'll kind of see how it plays out. So what do we need to know? Well, to evaluate this handle element, which is what we need to do to compute things, we first of all need to know this co-multiplication. So to do that, we essentially need to know a basis and a dual basis for V. So, well, writing down the basis is 1 and T. And now how do we write down a dual basis? Well, what is, our map, the form on V goes from V tensor V, and then we multiply, and then we take the co-unit. And so what is the dual basis with respect to that? Well, it's T comma 1. So if we multiply 1 and T and then evaluate, we get 1. And if we multiply the other way around, we, of course, also get 1. And the two cross multiplications both give 0. So now we can compute the handle element here. So what is this? Well, we start with 1, and then we co-multiply. So we go to the sum of, well, I guess I'll just write it out. So we have 1 tensor its dual element plus T tensor its dual element 1. And then we multiply those together, and we get T plus T. So we get 2T, and then we take the, and then we're just in V. So 2T is the handle element. So this is H. And so then we can compute Z of the genus G surface is just epsilon of 2 to the G T to the G. So what's that? Well, if G is odd, then we get 2 to the G if G is odd, and if we get 0 if G is even. So anyway, I just wanted to illustrate that this, you pick some Frobenius algebra and you can actually compute the invariance, and this particular one has the sort of weird property that it distinguishes all of the odd surfaces and none of the even surfaces, but such is life. And you can do the same with lots and lots of other Frobenius algebras. So I think I'll stop there, and then in the next hour when we come back, I'll start bumping up the dimension. So thank you.